Our next speaker is Dennis Darby. Dennis is Professor Emeritus in the Department of Ocean, Earth, and Atmospheric Sciences at Old Dominion University, and he's well known for his important insights into paleoclimate and paleooceanography of the Arctic and subarctic, and in particular, long-term changes in sea ice. And the title of Dennis's talk today is What Precise Source Tells Us About Arctic Sea Ice. Thanks, Dennis.
Thank you, Mary Lou. It's a pleasure to be here. And today I'm going to walk you through some aspects of sea ice and what we've been able to learn about sea ice from tracing its source, where it forms. We do this by the small amount of sea ice in the Arctic that has sediment in it. And first, before I begin, I have to admit that I don't do this work in a vacuum, and there's a lot of people I need to thank, including my own graduate students at Old Dominion, and of course my funding sources. So I'm going to walk you through different types of sea ice, and off the bow of the U.S. Coast Guard cutter Healy, our largest icebreaker, what you see here is very smooth, flat ice. This is what's referred to as first-year ice. It's usually no more than a meter or so thick. And there's a general absence of pressure ridges. And then what you see from an aerial view, from a helicopter, you see that expensive flat areas, first-year ice. It's a lot easier to break. It's weaker ice than multi-year ice. And here what we see is a picture of some multi-year ice. And the first thing you notice in here is there's these pressure ridges running through. You can see them all through the ice here. And interspersed, there's some smoother ice that's probably ice that's formed in the open leads as this ice moves apart and comes back together. The other thing I want to draw your attention to is the fact that this ice has sediment in it. Only about 5 or 10% of Arctic sea ice contains sediment like this. But look at how extensive this is. If you look off in the distance here, you can see that dirty ice extending off in a distance. And in two expeditions in 2005, the Hot Tracks expedition, and also in 2007 with the Swedish expedition, we ran into 3 different locations in the Arctic where we were seeing this kind of dirty ice for 3 to 5 days straight, 24-hour days of steaming, and covering somewhere around 300 kilometers of extent. So dirty ice can be very extensive in local areas and patches, and we'll talk a little bit about that later. The other thing that I wanted to show you is how large some of these pressure ridges occur. Pressure ridges are when ice comes back together again. It splits apart, and you have open leads, and when it comes back together again, it piles up. You can get pressure ridges that are generally speaking today, we only see them about 1 or 2 meters in height. But for every 1 or 2 meters up above the ice, it extends down several meters below. So you can run into very thick ice in the Arctic, and you're driving an icebreaker, you don't want to run into too many of these pressure ridges because it could really slow you down. Now this is today, and if you go back to the first time I was ever in the Arctic in '71, you can see pressure ridges in the back that are much larger. They look more like what you see here, that are upwards to 4 or 5 meters in height, and this is a rarity today, very large pressure ridges. So that's a quick run through of different types of ice scenarios in the Arctic. Now I'm going to talk a little bit about circulation, because circulation plays a big role in ice movement as well as the winds. But the winds dominate, but we still have to talk about circulation. And this is a map of the Arctic, and what we see here is some of the shelf circulation and deeper offshore. First, we see the Alaskan coastal current that comes up from the Bering Strait, and that comes around Cape Point Barrow. And it has other branches that go off even into Harrow Canyon. And then we have this East Siberian coastal current that comes along in that direction. And we have a longshore drift along Alaska that's real shallow. And then we have deeper circulation. And I'll talk a little bit about this. This is the Atlantic water that comes in off of the North Atlantic, and then it's warm, salty water but it sinks below the cold fresh water in the Arctic, and it resides around 200 to 600 meters down. And it comes around the edge of the shelf all the way around, and even along some of the major ridges. This is the Lomonosov Ridge here that splits the Arctic in two to the Eurasian and Amerasian sides, and we'll talk a little bit about that. And then you have this Beaufort countercurrent or undercurrent that comes along like that. So you get a very complex mixture of currents in the Alaskan area. And I wanted to talk about that because one of the areas, one of the sediment archives that we'll be talking about is this core JPC 16 that is taken right on the flank of the Barrow Canyon at 1,300 meters water depth, and it has extremely high rates of sedimentation. This was probably the longest piston core that was ever collected in the Arctic. It's 20 meters long, and the bottom of the core is only 9,000 years old. That means that it has a sedimentation rate of about 2.5 meters. It's almost as tall as I am every 1,000 years, which is phenomenal for sediment records in the Arctic, or anywhere for that matter. So that is a very complex story about why it has such high sedimentation rates. A lot of it has to do with these turbidity currents that go down the canyon, form eddies in the canyon, and then the fine-grained sediment comes up on the flanks and deposits there on a routine basis. It's not that fine-grained sediment that we're interested in. All that does is gives us bulk. What we're really interested in is the sea ice that comes around and melts and drops sand and other particles down into that sediment. And that only makes up about 1 or 2% of the sediment, but it gives us a fantastic record, as we'll see later. So I'm going to first show you some work of the Arctic buoy to show you the dynamics of sea ice transport. And what you're seeing here is these black dots are buoys or transponders that are put out on the ice, and then they're tracked over several months until they stop working. And so what you'll see is that you'll see a series of black dots. The first black dot here is where they drop the buoy. Then that's about every month or so, and then that's the red dot is the current location in September 1979. And so what we're going to show you is a record going about every 2 months or so from 79 to 2002. And you just watch these. Well, you're also going to see the shrinking and expanding of the thickness of the ice. The thickest parts of the ice is the white part here. And as it gets darker blue, it gets thinner and thinner until you get open water, which is actually almost navy blue here. So what you'll see here is you're going to see a general circulation of the Beaufort gyre, which is a anticyclonic circulation here, driven by a high-pressure system in the Beaufort Sea. And then you're going to see another circulation pattern called the transpolar drift, which comes out of Siberia here around the Laptev Sea and then swings across near the Lomonosov Ridge and out through Fram Strait. So let me start this video, and one of the things I want you to watch is don't get confused by the shrinking and expanding. That happens every season. But also just watch how irregular some of these buoys are moving. They basically seem to be just going randomly sometimes. So now you can see you're now in 1984, 85, 87, 88. We've had some different years, but if you see in the Beaufort gyre, things get, and you'll see new buoys appearing and disappearing as time goes on. You can download this video off of the web. It's under the Arctic Buoy program that Ignatius Rigger produced. And what I wanted to show you that is to show you that there's a lot of dynamic movement in the sea ice. It doesn't just follow these big patterns, which we are going to show you on a map, but it has a lot of random motion. And you have to understand that this is a monthly average. If you looked at daily movements, it's even more erratic. Okay, so the next thing I'm going to do is talk a little bit about, I have to introduce the Arctic and North Atlantic Oscillation. These are atmospherically driven phenomena that occur in the Arctic because they have a lot to do with, especially the Arctic Oscillation, with the ice drift in the Arctic Ocean itself. But the North Atlantic and Arctic Oscillation are two different phenomena that are highly correlated with one another. So they're actually measured, they have a somewhat similar point of measurement. They picked a point in the in the Beaufort Sea, and a point near Iceland, and a point near the Azores. The Arctic oscillation is defined by the pressure difference between the Arctic high pressure or pressure system and that near Iceland. The North Atlantic by that near Iceland and that near the Azores. So they're linked together in some regards. But these atmospheric phenomena do have an impact on weather, our daily weather. For example, when we go into a negative phase, it's sometimes referred to as the cold phase. We have weaker upper level winds that Jennifer was talking about, the jet stream. This allows for a lot of cold air from the Arctic to escape. And going into this last winter, we were pretty negative, and no surprise that although the Arctic oscillation doesn't control our weather always, but it does have an impact. We did have a colder than usual winter. When we get into the positive phase, these upper level winds are stronger. They're more controlled. There's not so much meandering in the jet stream, and the cold air is trapped in the Arctic. And we have basically a quite different weather pattern across the Arctic, across the globe. Atmospheric scientists have been arguing a long time about these oscillations as to whether they're really truly oscillations, because they don't see in the modern day record, the last 50 years, any good cyclic patterns that are statistical. So I've actually been corrected by atmospheric scientists, and they said, you shouldn't even call the Arctic oscillation an oscillation. It's a quasi-oscillation. And I think the problem is that atmospheric scientists are looking at just the instrumental record of the last 30 to 50 years, and us geologists, we're looking at records that go back thousands of years, and time has a nice filter effect, and it removes a lot of the noise in the record, and what we can see is something quite different. But getting back to its impact on circulation, here we see two extreme cases of the Arctic oscillation, one in 1979, where we had a very strong negative Arctic oscillation. The Beaufort High is very strong. You get an expanded Beaufort gyre, this area right up here, very large, and the transpolar drift is pretty much restricted to the Eurasian side of the Arctic. And then the other extreme here is in, 1994, and here's a very strong positive situation. And here the Beaufort gyre becomes very weak and disorganized, and look what happens to the transpolar drift. It swings way over towards North America. Well, this pattern is shown even more pronounced here. The red is the positive phase of the Arctic oscillation. This shows the surface drift in the Arctic during a positive phase. The yellow is the negative phase, where you have that expanded phase. And what happens here is that during the positive phase, you can get sea ice that originates over here in the Kara Sea, comes through Fram Strait, comes all the way over, swings over towards North America, can come all the way over here, and here's where our JPC 16 is located right here, can actually deposit sediment in that core location. Whereas during a negative phase, that ice is restricted to the Eurasian side, and it's almost impossible for that ice to get over to Alaska. So what I'm going to do is show you a record from that JPC 16 that shows the past changes of influx of Kara ice grains. And how we do that is that we use iron oxide grains because they are garbage bag minerals for trace elements. They form in igneous and metamorphic rocks tens of millions of years ago. None of these things are recent. They're all weathered out of or eroded from host rocks all around the Arctic. And basically what we do is we analyze each individual sand grain. The average size of these grains is about 1/10 of a millimeter, but they range from 45 microns to 250 microns. And we use an electron microprobe, and that's shown right here. We can analyze 5 elements at a time. We use 14 different elements, and we use that elemental composition like a fingerprint, and then we can trace each grain back to the source areas. And here you see the source data set that we use. It took me about 15 years to get all these samples from probably tens and tens of people that contributed samples to this data set. And we've clustered some of these samples into groups showing you major source areas. But we can trace each grain we have back to that entire database of 38,000 grains and match it up to a sand grain from a particular source area with less than 2% error. So we're very confident about our sources. And we use 8 different iron minerals and 14 elements. So we have a lot of variables to work with. And here's the record from JPC 16. The bottom line here is well, this is in years AD, so here's the modern 2000 here, and here's goes back to about close to 1,000 years before present. And here is the kilo years, and the bottom of the core is about 9,000 years old. And what we see when we look at the carat grains in this core is that anything but a uniform influx of carat grains. There's a lot of fluctuations in these. And the first time we looked at this data set, and by the way, our sampling interval is about 22 years. Every sample was taken every 4 centimeters. That's about 22 years time lapse between them. So we can look at decadal and scale at the smallest. We can look at annual cycles. But what we see here is that about 2,000 years ago, we had more than 4 times as many iron grains coming from the Kara Sea as we do today. What does that tell us? Well, you have to have a very strong positive Arctic oscillation, and it has to be very persistent for that to happen. So if we had a sort of what Jennifer was talking about, a climate system that was stuck in a very positive mode or in a what we call the warm phase, which you can get a lot of iron grains coming over from Kara Sea over a period of several decades and accumulating here. So what we see is, if we look back over the last 1,000 years or so, we see a big flux. That's this peak right here. And there were several big peaks right before that. This is the little ice age here. And then we're going back into this warmer interval, and we're seeing an influx of more iron grains from the Kara Sea. And when you look at climate change in the future and start projecting, we certainly have to take this phenomena into effect. And what we did was we did time series analysis on this. We used several different time series. The 0.99 confidence level is shown by this dashed line here. What we see here is some very interesting cycles. This one is 1,500 years, and that corresponds to Danskerd-Erskine cycles that were recognized in the Greenland Ice Core. And these are very important paleoclimatic cycles because we see this Danskerd-Erskine cycle throughout the glacial intervals, and it's a temperature fluctuation. We see this thing fluctuating in temperature, and it's right around 1,500 years. But the JPC 16 core showed several other significant cycles. 700 years here, 350 years, 280 year, 170 year cycle, and a 100-year cycle. So we have all these very significant cycles going on that we can decipher from this longer record that are certainly going to have an impact on weather and climate in the future. So now I'm going to show you some things about modern sea ice. So we're going to jump from a Holocene record, the last 9,000 years, to modern sea ice and what we can learn from looking at iron grains. What we see here is several photos that I took of sea ice, dirty sea ice in the Arctic. And one of the things that was really interesting about this dirty sea ice was its extent. We were seeing this dirty sea ice, as I said, over 3 to 4 days of steaming. Normally we're covering about 80 nautical miles in a day. So that's a large area that we're seeing consistent dirty ice. And in fact, during the Swedish expedition, they worked their things a little differently. I was not the chief scientist. You had to go to the Swedish Polar Secretariat that was on board to get permission to use the helicopter. And when I was running into all this dirty ice, I wanted to get out and sample it, so I needed a helicopter because they weren't going to stop the ship for me. And And after about 3 days of pestering this guy for the helicopter, which is expensive, I understand, he started hiding from me. I had to sort of find him. He was located somewhere hidden on the ship, so he wouldn't give me permission. But anyway, when you get out on the ice, we found really thick accumulations of ice, and we thought this was direct evidence of anchor ice. Anchor ice forms in less than 50 meters around the coastal areas, where ice actually starts to form on the bottom, attached to the bottom, and gets thicker and thicker until it gets thick enough that it's buoyant enough to lift off. When it does, it takes all kind of sediment with it, whatever's on the bottom. Most of the Arctic shelves are pretty fine grained, but you do get sand that comes up with that, and you get seashells like this right here, and even seaweed that we found. And we found this out in the middle of the Arctic Ocean. We were thousands of kilometers from land, okay? And here's a melt pond that you can see how some of that can get concentrated. But the other way in which sediment gets into ice is what's called suspension freezing. And this is in open water. It requires open water. And you have to have wave activity, and you get circulation patterns that supercooled water gets close to the bottom, ice crystals can form, and the sediment gets stirred up, and the ice crystals actually float the sediment to the surface. Once that ice gets to the surface, it forms slush ice, which then forms pancake ice. And that shuts down the process, because then it shuts down the waves, it shuts down the circulation, and it's self-limiting. So suspension freezing can be a very important process, but it doesn't give you high concentrations of sediment. It gives you very low concentrations of sediment. And we were seeing high concentrations. And there was a bias involved here, because when you're up on the bridge of an icebreaker and you're looking for dirty ice, you're not going to see something that's a few milligrams per liter. You're going to see something that's kilograms per liter. And so more likely than not, you're going to stop the ship or go sample anchor ice deposits. And when we did this, we found something fascinating. And it was really puzzling at first. 2/3 of the samples we had looked like this. There was one source, and one source only, that was significant, and this one here. But we found at least 1/3 of the samples contained one source, and this was from North America, and here's a source from Russia. When sea ice entrains sediment, it's going to entrain it from one locality, not two. It's a self-limiting process. Even with anchor ice, when it lifts off, it just has the sediment from one site. So how are we seeing sources from two different disparaging areas that are thousands of kilometers apart? And the answer for that is when these ice flows mingle, there's a lot of dynamic separation of the ice and coming back together again. It's like a jigsaw puzzle out there. And a good friend of mine, Don Perovich, showed me a slide. And I was trying to get it from him, and I ran out of time. But he showed me a melt pond with a sharp line right down through them. One side of it was dirty ice, and the other was clean. And it was just a sharp demarcation. And that was where ice had separated, broke apart, and came back together again. It didn't come back together again where it was. It came back together with different ice. So you can get mixing of ice quite frequently. And that's what we're seeing out here. So now I'm going to take you back into the past again, and we're going to look at a fascinating core. This is the ASEC Score. ASEC stands for the Arctic Coring Expedition. This was the first and only time that the ocean drilling program took a drilling rig into the Arctic. It was a very expensive proposition, required a Russian nuclear icebreaker and a regular icebreaker, the Odin, just to keep this platform in place, because sea ice is moving all the time, and they have to be able to stay put for days on end without moving. And they were able to drill several drill holes and composite it down to about 400 meters depth. It gave us a fantastic record of the past 50 million years of sedimentation in the Arctic. I'm going to show you that story in a second. And then I'm going to jump over here to the Fram Strait and show you a much shorter record that goes back only about 40,000 years. And this is the polar stern box score 1230. So first, the ASEC score, and this is what we're looking at here is the maximum number of grains from any one source from all around the Arctic that was the maximum number of grains from any one source, okay? And these sources have to be more than 1 year ice drift from ASECs, from the core site. And we did this with a very conservative approach. We said, well, we don't know what the circulation was like 40, 30, even 20 million years ago in the Arctic. You can only assume maybe it was similar to the Beaufort gyre and the transporter drift, but you can't be certain. And you also can't be certain about the ice drift. Today, the average drift of ice is about 3 centimeters a second. And now it varies quite a bit depending on location. Near Fram Strait, it could be 12 centimeters per second. But in other places, it could be much less. And not only that, but the ice can reverse directions a lot. And so it goes backwards. So we said, okay, forget about that. We're going to just say that it's moving 5 or 6 centimeters per second. And instead of it following the circuitous tracks that it does today, we're going to say it just starts at the shelf and goes straight towards ASECs without deviating. Doesn't reverse, doesn't jiggle around at all. So we're only looking at sites that were far enough away from ASECs that it would take more than a year. Because if it takes more than a year, the ice has to summer over. It has to be there in the summer. That means it's perennial. So what we're looking at here is a record of perennial ice. In other words, ice that exists in the Arctic year-round. And what we see here is a fascinating record. Going back to about 50 million years, we see no ice rafting at all. These are samples that are just devoid of iron grains. And then we get up here and we see this big jump. And that jump occurs at about 44 or 47 million years, depending on which age model you use. And I don't want to get into details. There's one age model. Here's the old one. This is the newer age model that's been proposed. They're very similar except in this area. And what happened here was really interesting to us because the perennial ice conditions didn't last long. Each sample there is about 70,000 years. And, so we didn't get a very close sampling like we did in JPC-16. ASECs had a lot of demand for samples. There were thousands of people trying to get samples. So we only got samples spaced out about every 50 centimeters. But even with that record, we could see that it didn't last for more than 100,000 years, for sure, and probably a lot less than that. We went back to seasonal ice. And then it came back again several times. And this whole period between 44 million years and about 37 million years is a period of unstable conditions in the Arctic. Now, you have to remember that the Arctic reached its maximum, actually the Earth reached one of its maximum temperatures about 50 million years ago. And now we're just 6 million years later, we're seeing perennial ice in the Arctic. And it's fluctuating back and forth until you get to about 37 million years ago, and then we have pretty much continuous perennial ice. The interesting thing here is that the ice sheets on Antarctica didn't start till about 34 or 36 million years ago. So that means that there was perennial ice in the Arctic before major ice sheets started to develop in Antarctica. And we're also seeing that Greenland may, in fact, have had ice on it much earlier than we thought today. And that's another subject that we're working on today. But that indicates to us that perhaps the Arctic, instead of just responding to temperature change and global climate, the Arctic may, in fact, have played a role in changing climate. And because we know that once you have perennial ice up there, you have ice in the summer, it reflects, as Jennifer showed us, a lot of the solar radiation, and it can cool the globe down significantly. Now, we don't see it returning to seasonal ice until this crisis called the Messinian crisis, and for those of you who are not paleoclimatologists, this is when the Mediterranean Sea dried up. That's about 6 million years ago, and for some reason, circulation changed, and we went back to seasonal ice for an extended period of time. Then it went back to perennial, and then in the last 1.5 million years, we get into the Ice Age, when we had ice sheets developing and disappearing, and we had a really large fluctuations in climate, and here we see seasonal ice returning several times during the Pleistocene, the last 1.5 million years. So that's the ASEC story, and here's the Fram Strait story. And now you're looking at a much more recent record. It goes back to maybe 50,000 years or 40,000 years at most. These are thousands of years. Or excuse me, over here is thousands of years. I'm having a hard time even reading mine. It's about 30,000 years. So we're looking at about the last 35,000 years. And this is the ice, iron grains that have been traced back to the Banks Island area. And we know that that's where major tongues of the ice sheet in northern Canada flowed into the Arctic Ocean. And then there was this lesser ice sheet called the Inuition that covered the Canadian islands, the archipelago. And that ice sheet also calved off icebergs. And lo and behold, we could look at different events here where ice rafting, large amounts of ice-rafted detritus was making it through Fram Strait at almost identical times as there was large armadas of icebergs coming out of Hudson Strait in Canada, flowing down through the Labrador Sea and out into the North Atlantic, all the way over to England, and depositing sediment all the way across the North Atlantic. And these things are almost identical in timing to those Heinrich events in the North Atlantic. And we can see them. So not only was there a North Atlantic event, but there was an Arctic event that coincided just as well, going back at least to Heinrich event 4. Okay, I'm going to finish up now with a little story about the Greenland ice sheet, because that's been in the news a lot. We have been startled by the rapid disappearance of ice in Greenland. And the question comes up is the ice rafting or ice calving off of Greenland been a uniform factor and just increasing in the last few decades, or has there been cyclic fluctuations? So here we see the green shows us the pattern of ice rafted detritus that's been traced back to the East Greenland ice, and that's where most of the big icebergs come from. The one that sank the Titanic came from that area, probably. And we see anything but a uniform calving rate over, what? This goes back to, what, 1890 or something like that. So the 1800s, it's last 120 years or so of a record. So every decade or two, we see an increase in ice rafting. And we can see a similar thing with our iron grains from a core off of South Greenland. And here we see, I can trace back to individual parts of the Greenland ice sheet. The red here is South Greenland, and the black is East Greenland. They're pretty much in synchronous. There's a little bit of lag and lead to each one, but that's minor. And what we see here is a 15 to 30-year cycle, more or less. We don't have a long enough record, and we're working on a much longer record that we'll be publishing later on, and we'll do time series analysis on it to see. So the take-home story here is that the Greenland ice sheet is anything but a continuous process of calving. It's very cyclic. So these cycles are imposed upon modern global warming. And now, that means that when we get to a peak in one of our cycles, and we have global warming going on, we're going to see probably maybe an enhanced diminishing of the Greenland sea ice. And of course, this has major implications on sea level, especially to folks like myself, that my house is 17 feet above sea level. I live in Virginia Beach, and we're the second most vulnerable area in the United States when it comes to sea level change. New Orleans is the first. So we're right behind New Orleans as far as being vulnerable to sea level change. So it's a big concern to us. And now I'm going to leave you with a picture of pancake ice. And I don't know how many people in here have ever seen pancake ice? Okay, just a few. So here's a shot of pancake ice. That's what it looks like. And I want to thank you.